In this episode, we are going to be a lot more functional. It's still going to be object-oriented, but this time we are going to use a lot of the functional features of JavaScript. And we are also going to write a really useful utility function called groupBy that you can use in any of your projects. We are going back to solving the standard version of Conway's Game of Life. Quick reminder, Conway's Game of Life operates on an infinite grid of cells, and each cell is either dead or alive, unlike Schrödinger's cat, which can be both. So we have this infinite grid of cells, and the task is to calculate the next state following a set of rules. A cell will be alive in a subsequent state if and only if one of the following three cases hold. The cell is alive and has two neighbors that are also alive. Or the cell is alive and has three neighbors that are also alive. Or the cell is dead but it has three neighbors that are alive. In all other cases, the cell will be dead in the next state, but it will always live in our hearts. Let's dive in. So this time I would like to start with establishing how our data structure works. So let's start with a test that makes sure that our 00 cell is dead when the new port is created. This test obviously fails, and to fix it we first need to create the board, the cell, which will have x and y coordinates, and also the isalive function. Now it already compiles but it returns undefined instead of false. The next test is going to make sure that we can spawn a cell. At this point the test is already failing, so we need to create this spawn function next, and we can continue by writing the expectation. Now to fix this test we just have to introduce a new field, set it to false to begin with, and then in spawn we change it to true, and in isalive we will return this. Now of course at this point we are still not taking into account what is the cell. Actually we are not even taking the parameter here. So if we spawn one cell, then all the other cells are going to be spawned at the same time. So let's do something about that. So we are going to write a test that makes sure that if we spawn one cell, say the 3, 5, then it doesn't spawn another cell, for example the 0, 0. So to satisfy this test, first we need to make sure that we store the x and y values for the cell. So now that we have the x and y coordinates available, then we can just create a string that identifies that specific cell, set that key in an object to true, and then use the same key in isalive. This still fails on two tests because if a key is not set ever, then it will be undefined by default, but we can fix this by adding a double bang, and the undefined will turn into false. Obviously this screams feature envy. This looks at like a string representation of the cell, so let's move it onto the cell. But since toString is the default way for JavaScript to cast an object into a string, we can actually just remove this toString function and just write cell. Okay, now we are done with this setting up the board, and actually I'm going to create a separate group for these tests describing the board. Now we can actually start writing tests that describe the evolved function, which will take a board and return an evolved version of that board. So the first test is just going to test that our empty world evolves into an empty world. To fix this test, we just create the evolve function first, and then we need to make sure that we return the board, which of course can be the original board. Now that we are done with this, there are a couple of things that start to annoy me when looking at the test. So let's do a bit of refactoring. First, I will create a cell function to remove some of the clutter when we create cells. Also, I will move the board creation into the before each. So last time we could just create a simple function expect that, but that actually used the board that we created in the before each. And now we are not always testing the same board. Sometimes we have another object because we are not mutating the board, but we are creating a new board. And because of that, we actually have to write a slightly different expect that. So the trick is that we are going to return an object that has an in function, and that is the function that will actually do the expectation. The benefit is that now we can write expect that cell 00 in board and expect that cell 00 in evolved board respectively. And the only one that we didn't switch yet is this one, because this is about alive, so we need the same function for expect alive. But instead of duplicating this, I'm going to write another function and generate the two functions from that one. Okay, now we have a really nice domain-specific language for writing our tests. So let's continue with the next test, which will make sure that the lonely cell dies. Since all of the cells at this point that we tested were dead, we can just use an empty board. Now this is where things start to get interesting, because now we have to test that a 00 cell with two neighbors actually survives. We first extract a variable, and then we need an if statement that will make sure that we spawn the 00 cell only sometimes. Now last time we actually checked one specific cell, but this time let's do something slightly different. Let's take the values stored in our object alive and look at the length of this array. If the length of this array is exactly 3, then we are going to spawn. Why is this solution interesting? Because if I write -1 here for the 00 cell and make this 2, then this is actually the number of neighbors the 00 cell has, because all of the cells that we spawned were within the 3x3 neighborhood of the 00 cell. So let's just extract this into a variable called count neighbors, and we are going to use it, basically fake it till we make it. Okay, so the next test could be to test if a cell with 3 neighbors survives. Satisfying the test is really easy now, because we just write neighbor count equals 3. It took me a bit of time to figure out the next case, because what we need to realize is that the dead cell with 4 neighbors will spawn with the current code. And for now that fails, but the fix is really simple, because we just have to make sure that we don't subtract when the 00 cell is not alive. Now of course that breaks some other cases. For example, right now if we have a cell with 2 neighbors, it's going to spawn, so we have to write a test that it doesn't spawn. For now I'm deliberately going to write this in a way that blocks spawning of cells with 3 neighbors, so that I have to write an extra test to make sure that that behavior is documented as well. So then let's write that test for the spawning rule for 3 neighbors. Now of course the fix is really simple. Alright, so the interesting part is that this solution works perfectly as long as we are just looking at the 3x3 center. But we actually want to make sure that if someone spawns a cell outside of the 3x3 bounding box, it doesn't affect the 00 cell state. So let's write a test that makes sure that, for example, 3,5 doesn't count as a neighbor of 00. So to fix this test, I want to filter this array for the actual cells that are neighbors of 00. Unfortunately for now, we are just storing truths in this. So why not just store something useful like the cell itself? And once we have done that, then we can do a filter. And in this filter, I will take the cell and I will check if it is included in the list of neighbors for 00. Now of course, equality between objects is a strict equality in JavaScript. So instead I will use this toString value here. So now I just have to list all of the neighbors of 00 one by one. Okay. So now this satisfies the test, but actually I still have among the neighbors the 00, and I have this quirky thing here. So let's get rid of this one and this one to simplify our code. A further simplification is that I'm going to move a couple of things into other objects. For one thing, I would want this object values board alive to be on the board as a list function. The second thing is I'm going to move this list onto the cell to make things easier. But this neighbors function should actually return the cell objects. It's kind of weird that it it's returning strings, so let's modify it as such, and then we will do a simple map here. Okay, so now we have actually solved part of the problem, but we still need to make sure that other cells get spawned and kept alive when they should be spawned or kept alive, because right now we are only dealing with 0, 0. To drive this behavior, I will write a test that makes sure that 3, 5 with 2 neighbors stays alive. So to satisfy this test, we could either duplicate this whole thing, but actually I'm suggesting a different solution this time. And for that, I will first start by refactoring a bit. So I will turn off this last test. Everything is green except for that one last test. And I'm going to refactor this into an object, and the keys on this object will be the toString values of cells. Okay, then so let's go back and let's try to satisfy this test now. Now if I just duplicate this part with 3, 5 and also this part and modify it to 3 and 5, then it fails. And the reason it fails is because we didn't quite finish this neighbors function. So we actually need to add this.x plus, and then here I'm going to just replace this with a minus, and then also here we need this.y plus, and just remove those minus ones and replace them with simple minus, and that actually passes. So how could we refactor this? This part is simple because here we can just take the cells in the board and simply go through those cells. So this doesn't work because if a cell wasn't alive and it was spawning now, then it won't show up in this list, but it will show up in the list of neighbors of living cells. And to generate that, we are going to use a flatMap.
Wait, what is flatMap? So map is a function that operates on an array and applies a function to each and every item in the array. For example, if I map the array 1, 2, 3 with the function that multiplies by 2, I get 2, 4, 6 as an array. Now if we take the array 2, 6, 25 and map it with the function that returns the prime factors of a number, we get this weird-looking beast. Sometimes though, we just want to have that as a simple array containing 2, 2, 3, 5, 5. One solution to that is to use flatten, which turns an array of arrays into a single dimensional array. It just removes a bunch of braces. Flatmap is the combination of these two functions. First it maps the array, then it flattens. Incidentally, this is just the thing we need if we want to generate a list of all neighbors of a list of cells. We take the list of cells, map each of them to a list of their neighbors, and flatten. Now that this is clear, let's head back to coding.
Now one thing that might be interesting here is that there is an if statement within a for each. So why not just move this if statement into a filter? And now that we did that, how about we use reduce to fill up the new board? What can make this even nicer is if we do the spawn function, made sure that it returns this, then we can just return the result of spawn and get rid of some braces and returns. Okay, so this part is still ugly and we are still not generating all of the cells that we want to. So how could we do that? So to generate the neighbor counts, I'm going to use again the list of cells in board, and again I'm going to generate their neighbors with a flat map, but then I will use a reduce. I will start out with an empty object, and in each step of the reduce I will take the accumulator, add 1 to the key that is represented by the cell, and then return the new accumulator. Of course I have to think of the case when the key is not in the accumulator yet, so I first test if the accumulator already has that value. If yes, then we add 1, otherwise we just start out with 1. So this is actually the complete solution, but we can make it slightly better, because
we still have this board list flatMap twice, and this reuse is very specific and hard to understand. So to clean this up, I will actually write an extra function and then use that extra utility function to rephrase this in a nicer way. So that extra utility function is going to be groupBy, and I'm going to monkey patch this onto array because it's just such a useful function that it comes up all the time, and I wonder why it's not in JavaScript to begin with. So let's add it now. So the first test is really simple. We just take an empty array, group it, and then it should actually be an empty object because there are no groups. We will also have a callback which takes an item and then generate a key for the item. For this specific code we won't need that callback, but to make this generic I'm still going to implement it this way. To fix this test I will just create a new function and make it return an empty object. The second test is going to make sure that if there are distinct elements in the array, then we get a hash with a separate key for each of the elements. We are going to do a reduce just like in the evolve function that we previously implemented. We start out with an empty object, and we add a new item to the object, the value for which will be a single element array with the item in it, and we return the accumulator. Now the next interesting test case is when we actually have duplicated elements. So basically we create the key when it's not existing as an empty array, and then we push the items one by one and return the accumulator. Finally, we need a test that makes sure that we are actually using the callback function when it is passed in. So now that we have the groupBy, we can use it to refactor this code into something slightly different. So I'm going to start by grouping the neighbors. So now that I have the groups, this is actually a hash, but I only need the values from it. So I'm just going to say object values here for this whole thing, and this will be arrays for each cell that is a neighbor of another cell. It will contain that cell as many times as many neighbors it has. So I'm going to use that and map it, and I'm going to return an object with two keys. One is going to be the cell, which is this first element of the group, and the other one is going to be the neighbor count, which is the length of the group. Now using that, I can just do the filter and do something very similar than this one. Instead, this time I will get as an input this object with two keys. So let's disassemble that into two variables in it, and then I don't need these here anymore. And finally I can just go ahead and do the reduce directly. The only thing I have to pay attention to is that now I'm not getting a cell but an object which has a cell key, and that's it. Now actually I will extract this into a variable just to make it easier to read. One last thing that could be nicer is this object values is weird and it's out of context because you actually have to check where the other end of this parenthesis is. Unfortunately, there is a reason why object doesn't have a values function, and it's because then it would be a key that clashes with a potential other values key. But there is a way around that, and I actually like adding one more function on array prototype, and that function is the list groups by, and it's basically just the group by function wrapped by object values. And then if I do that, then I don't need this anymore here, and just say list groups by, and that's it.
So let's summarize what our algorithm does. It takes the list of living cells. From that, using the flatMap function, it generates a list of neighbors of living cells with duplicates when a cell has multiple neighbors. Groups identical cells using the list groupBy function we implemented. Based on the groups, it calculates the number of neighbors for each cell that has at least one neighbor. Uses the filter function to select only cells that stay alive according to our rules. And finally, generates the state using the reduce function. I particularly like this solution not only for its simplicity, elegance, and style, but also because it is a very efficient way of calculating the next state in the game of life. Alright, the final code is in the description as always. If you enjoyed this episode, consider telling others about it and check back for later episodes. Until then, keep coding and carry on.